The other part is radiation dose, radiation measurement. That's a new topic. In radiation measurement, we have a few terms to understand. First, radiation dose, or we also say the absorbed dose. So the radiation dose, that means the energy liberated by radiation by a material is known as the radiation dose. So that's the simple definition. Now, when we have a radiating body, that will radiate radiation, right? And it is energy. So that energy released by this material, we call it as the radiation dose. Okay. And there might be some material which will get irradiated. Irradiated means it is receiving the radiation or it is absorbing the radiation energy. So that type of radiation we call as the absorbed dose. So if an object releases the energy, it's radiation dose, and if it absorbs energy, it's absorbed dose. Okay. The unit we use to measure radiation dose is measured in gray, and the units for gray is GY, capital G, simple Y. And if we look at the definition of gray, a gray is energy liberation of 1 joule per unit mass of the material, or it is 1 kilo of object absorb 1 joule of energy by radiation. Was the definition clear? No, right? No. So let's look what's 1 gray once again. When I say 1 gray of radiation, that means let's think of an object. Let's think of an object which mass is 10 kilogram. Okay, the mass of that object is 10 kilogram. When we radiate energy, or when this is exposed to radiation, each kilogram, so here we have 10 kilogram. In this 1 kilogram portion, it is going to absorb 1 joule of energy. It is going to absorb 1 joule of energy. So in total, this body would have absorbed 10 joules of energy. Okay, in total, this would have absorbed 10 joules of energy, but we are not going to talk about this entire body. Instead, we are only interested about 1 kilogram of this body. So 1 kilogram of this body absorbs 1 joule. Then we call that radiation as 1 gray. Is it clear? So if we have 1 gray of radiation, each and every kilogram will absorb 1 joule. So if the object is 10 kilogram, it would have absorbed 10 joules. Now let's say a human who is around 60 kilogram, he is exposed to 1 gray of radiation. Then how much energy is absorbed by the body? How much energy is absorbed by the body? How much energy is absorbed by the body? So did you get the definition clear? 1 gray of energy means 1 kilogram of his body, it will absorb how much? It will absorb 1 joule. So his body is 60 kilograms. So each and every kilogram absorbs 1 joule, then in total his body is going to absorb 60 joule. Is that clear? Saja and Taiba? Okay, so now let's go through the definition once again. Now you have to be clear. Each kilo of object absorb 1 joule of energy by radiation. So that statement is clear, right? Now let's look the other definition. The other definition says energy liberation of 1 joule per unit mass. So here it says energy absorbed. Here it says energy liberated. So both of them are contradicting ideas, right? So it's actually the point of view. Now, from the point of view of this object, that means it has absorbed. From the point of view of this object, it has absorbed 1 joule. It absorbed 1 joule per kilogram. In point of view from this radiation, it has released 1 joule of energy per kilogram. So from the point of view of the radiation, it has released 1 joule per kilogram. So is that clear? Now, a gray is energy liberation of 1 joule per unit mass of the material. Or each 1 kilogram of the object absorb 1 joule of energy by radiation. So 1 gray is equal 1 joule per kilogram. Is that clear? Next, dose equivalent. Now just think, when we were talking about radiation, there are a lot of type of radiation, right? X-rays, gamma rays, and then we had electron, then we had slow neutron, fast neutron, proton, alpha. We had a lot of them. Then, can you remember X-rays? X-ray were just ray. It actually was just electromagnetic radiation. And then how about this alpha? Alpha was the helium nucleus. So, both of them may be 1 gray of radiation, but the effect due to this X-ray and alpha, are they same? No, right? This is just electromagnetic radiation. So it will pass through the body. Its harm is less. But this is alpha particle, which is larger in size. It cannot go through the body. It cannot penetrate. So it is just like hitting your surface or your skin. So which one will cause more damage? X-rays or this alpha rays or this alpha radiation? Which one will cause more damage? Obviously, alpha is going to cause more damage, right? Than X-ray or gamma ray. Although both of them are 1 gray of radiation. So that is why we introduce a new term, dose equivalent, okay, or the effective dose. So here what we do is we consider how much effect that each and every radiation has. So what we do is we multiply absorbed dose by a quality factor, or we call that as the relative biology effect. So X-rays, we consider it as 1, and than X-rays, electrons, its effect is high. Than electrons, slow-moving neutron has high effect. Than that fast-moving neutron and proton. and finally alpha. So the idea of dose equivalent, is it clear? I think I have to ask from here. Are you clear with radiation dose and absorbed dose? So next, so we have radiation dose and absorbed dose. So radiation dose means how much radiation energy an object releases. Absorbed dose means how much it absorbed, how much other body absorbed. So from here, we describe what is 1 gray. So the definition of 1 gray, I explain what is that. I hope it's clear. And then I'll clear why we went from absorbed dose to dose equivalent. What is the reason? Because although we have 1 gray of radiation of gamma, X-ray, and alpha, both of them do not have the same effect in organism. So there's a relative biological effect. Alpha is going to cause more damage. To include that, that is why we introduced this dose equivalent, which is equal quality factor time absorbed dose. Okay. So that's the summary. And the permitted dose of radiation per year is not 50 million sieverts. It is 50 millisieverts. Okay. So it's millisievert. And this dose equivalent, that is measured in sieverts. Okay. Absorbed dose is measured in gray, and when we multiply it by the quality factor, it becomes dose equivalent, and we use sieverts to measure that. So the permitted dose of radiation per year is 50 millisieverts. Clear up to this? So shall we move to the next part, particle physics? So particle physics, we are going to study, we study about the elementary constituent of matter and radiation and interactions among them. All this time, we might have thought that protons and the neutrons were the smallest particle and then electron. But actually, this proton and neutron can be further divided, okay? Further divided into small parts called quarks. So we are going to study about these small particles and the interactions among them. So that is called as particle physics. And this particle physics, it is also known as high energy physics because these elementary particles can only be detected during high energy collisions, which is done in particle accelerator. Particle accelerator means we accelerate the particle, we accelerate the proton until it gets divided into smaller elements, these quarks and all. And we can only identify or detect these quarks during high energy collision. That therefore we also call them as high energy physics. So just know the name. Okay. In nature, we have only 4 types of forces. Whatever force we discuss can be classified into these 4. So strong nuclear force, electromagnetic force, weak nuclear force, and gravitational force. So we also have ordered in the strongest to weakest order. So strong nuclear force, that is between proton, neutron, and proton. So within this nucleus, electromagnetic force, that is all around us, and gravitational force, it is also around us. We know what's the gravitational force. And weak nuclear force. I will check about this and let you know where we can find this weak nuclear force. Okay. So uh, we said that, give me a minute. Okay, I mentioned that we have small particles, right? Elementary particles. That is not uh, protons or neutrons, which is further divided. We can classify these particles fermions, into fermions and into bosons. These fermions, they are the one who make up the matter. Make up the matter. And bosons, they are the reason for the interactions. Okay, interactions among the particles. So this is more like the ones that attract. So for example, we have these types of forces, right? We said we have nuclear forces. Between two particles, there might be nuclear forces. There should be something shared among them, right? To have that force. So this is due to bosons, and these masses are due to fermions. Okay, these mass particles are due to fermions, and these interactions are due to bosons. So did you get an idea about what is fermions and what is bosons? What are their duty? So bosons duty is to interact among the particle, and fermions are the one who actually make up the particle. And these fermions, we can further classify them into leptons and quarks. Leptons and quarks. So quarks are those who participate in strong interaction. In strong interaction. And leptons, they do not participate. Do not participate in strong interaction. So what is this strong interaction? I was talking about nuclear force, right? So nuclear force is strong interaction. So between proton and proton, we have strong interaction. How about the nucleus and the electron? Do they have strong interaction? Does this electron involve between strong interaction? Yes or no? What is the type of force between the nucleus and the electron? Is it the nuclear force, strong nuclear force, or electrostatic force? It is the electrostatic force, right? So the electrostatic force, is it the strong interaction? No, it is the electrostatic force. So it is not the strong interaction. Therefore, does the electron involve in strong interaction? No. So electrons are example for electrons. They are the example for leptons. Okay, they do not involve in strong interactions. And then we have quarks that are within the proton. So the proton is made up of quarks. So those quarks, they have strong interactions. Okay, so did you get an idea about what is leptons and what is quarks? I will clear with this classification. So I'll just tell how it is classified. Okay, bosons and fermions, that is classified by understanding here they make up the matter. This is the particle that actually make up the matter. Bosons, they are just used for interactions. And those who make up the matter, they are also of two types. Some of them involve in strong forces. They involve with strong forces. Those who involve with strong forces, we call them as quarks. And those who do not involve with strong forces, we call them as leptons. Okay, so that is how it is classified. And up to now, we have found a lot of type of quarks and leptons. So the names are interesting. And the tables is also easy. How we have ordered them is also easy. So here we have quarks. The name of the quark is interesting. Up, down. Okay, up quark, down quark. The other one is charm, strange, top, bottom. So these are quarks. And this quark has charge plus 3 by 2. And these quarks has charge minus 1 by 3. So these quarks have minus 1/3. These quarks have plus 2 by 3. And this block is of quarks. And then we have leptons. So this block has 0 charge. And this block has minus 1 charge. So here we have electrons. This is electron. This is muon and twan. And we call this as neutrino. So this is electron neutrino. This is mu neutrino. This is tau neutrino. And here, this classification, we call them as leptons. These two together, it is the fermions. Okay. Both of them combined is the fermion. So this over here is the fermion. And this block is for bosons. So this is photon, this is gluon, Next we call as Z boson and W boson. So this is photon and this is gluon, Z boson and W boson. And this first generation okay, so this is Z boson and this is W boson. And this group, this is this group, this one we call the first generation, the second one second generation, and third generation. So the second and the third generation are unstable. You only have to know about the first generation. Okay, first generation is only stable. I know the names might be confusing and the charges might be confusing. So I'll tell how you can remember. You only have to remember this first generation specially. Okay, so this is not hard, right? Quark, the name for quark is not hard. Up, down. So when you put this into these boxes, here you have up and down. So up has a positive charge, down has negative charge. And then we have in leptons, we have uh, electron and electron neutrino. Okay, we have electron, and this is electron neutrino. Neutrinos are neutral. Electron, we know the charge is already -1. So here in these bosons, you have to remember photon, especially, and gluon. Okay, the others are easy, right? Z and W bosons. So then how is, so here second and third generation is unstable, therefore they decay into first generation. Okay, in addition, each fundamental particle has its own antimatter. So we were talking about neutrino, right? And also I was talking about antineutrino. And we were talking about electron. Its antiparticle is positron. Like that, if we have up quark, we also have an anti-up quark. Down quark is, it has its anti-down quark. So just like that, all these particles have their antiparticle. Okay, that is mentioned in this first note. Composite elements formed by strong interaction of forces between quarks are called as hadrons. So hadrons mean now these quarks are going to combine among themselves, right? Not these, all these quarks, sorry, the up and down quarks, especially these up and down quark, they will combine to form some other particle. So that particle we call as hadrons. And if 3 quarks combine, they are baryons. So for the examples for them is proton and neutron. So look, proton has 2 up quark and 1 down quark. So look, the charge of up quark is plus 2 by 3, plus 2 by 3, and minus 1 by 3 down quark. When you add all of them, come to plus 1. Similarly, neutron. In neutron, we have 1 up quark and 2 down quark. So that down quark, when you get the charges, it becomes 0. Okay. If 2 quarks combine, we call them as mesons. Examples are pions and kaons. Other than the name, just forget about the name. Okay. You have to have a general idea, but especially in this part, what you have to know is you should know how to classify. Okay. You should know how to classify into this table. That is one part. And next, what you have to know is you have to know how many up quark there are, how many up and down quarks are there for proton, and how many up quark and down quarks are there for neutron. Okay. Those are the 2 important parts you have to know under this. Is it clear? Sometimes you might not remember these values and all, but you might have got the idea. If you have got the idea, that's enough. Later you can try some questions to get this part clear. And remember, in this table, in this direction, mass increases. Okay. So charm quark is heavier than up quark. Top is heavier than charm. Clear? So with this part, we only have linear accelerator to discuss. I'll try to make a video for linear accelerator because you can understand that by looking the video. This particle physics and what we discussed earlier, nuclear fusion and nuclear fission, that in a live session only you will understand much better. So what we discussed finally, particle physics. IL, okay. If you have any doubt, you can ask. If not, we can end the session, but you can just go through this video once again. Later, if you get any doubt also, make sure you ask them and get clear. Okay. How about the others? Sarah, Shaham, and Taiba. Okay, I'll end the session. Assalamu alaikum. If you have any doubts, make sure you ask them, okay? Because I know at once itself, you cannot come to a decision whether you understood or not, because this is completely theory. So when you check this video once again, or when you go through this note once again, then only you will understand if you have any doubts or not. For now, you might not have a clear idea, okay? So just go through, and if you have any doubts, make sure you ask them and get them clear, okay? I'll end. Assalamu alaikum.